In the last two videos, we saw a quick introduction to differentiation and how to differentiate polynomial functions. So that's when we had different powers of x. Now, it's not always powers of x that we might have. So, for example, in engineering, quite often we think about how things vary with time. So, if we have a displacement, let's say s, do you remember s is the letter we use for displacement from our CVAT equations? If we know that the displacement of something varies with time, such as, I don't know, 3t to the 4 take away 2t to the 5, we now have an expression. We now know exactly how the displacement of that object changes as time changes. Right, so if I wanted to work out the velocity of this object, I can't just use the CVAT equations because I don't know whether the acceleration is constant or not. In fact, I can see that it's not, but we'll come back to that later on. So whenever we've got one of our engineering sort of terms, like here displacement, given to us as an equation in t, that's a little hint that we might need to use differentiation or maybe integration, as we'll see in the future. Okay, so how does this work? Well, we still have the same rules. So if we need to differentiate, we still got the same rules. We want to reduce the power by 1, and we want to multiply by the old power. The only thing is, instead of x's, we're now considering the powers of t. But otherwise, it's more or less the same. All right, so what happens if we were to differentiate differentiate displacement with respect to time? Well, if you remember from one of our earlier videos, we kind of talked about this as velocity, didn't we? Velocity is how displacement varies with time. So in terms of differentiation, if we ever want to know velocity, as long as we know an equation for the displacement in terms of time, we can differentiate it. So what did I have over here? 3t to the 4. So let's say we had s is equal to the same thing, 3t to the 4 minus 2 times t to the 5. Let's say I wanted to work out or find out what the velocity or the equation of the velocity would look like. Well, to get v, I would need to differentiate s with respect to t. So remember those two rules, reduce the power by 1, multiply by old power. So let's do this term by term. So reduce the power by 1, 3t cubed. Right, 4 take away 1 is 3, and then multiply by 4. Let's repeat this with the second term. I've got 2t to the 4 now. Power goes down by 1. Multiply by the old power, so multiply by 5. And I've still put a minus sign here because that's what I had over there. So my velocity is going to look like 12t cubed minus 10t to the power of 4. So I've got an equation describing how the velocity of my object changes as time changes. Okay. Now another way to think about this is the gradient of the displacement time curve. Right? If I was to show this on a graph, the gradient could be described by this equation over here. Right. So we've got differentiation linking our displacement and velocity. Well, we could do the same with acceleration. So let's say I wanted to find the acceleration of the same object at any time. Well, we could do that by differentiating our velocity with respect to time. So acceleration is the differential of velocity. Okay, well, let's do that then. So A is dv over dt. And if we follow those same rules again, we have 12t squared, but I need to multiply by the old power, so 3 times this. Here I'm going to have 10t cubed. I need to multiply by the old power, so multiply by 4. But I mustn't forget the fact that I've got a minus sign, so I'll put the minus sign there again. So my acceleration would be, let's tidy this up, 3 times 12, 36t squared minus 40t cubed. So I now have an expression for my acceleration in terms of t. Now, if I wanted to find out the instantaneous velocity or the instantaneous acceleration, so the velocity or acceleration at any particular time, all we need to do is substitute in the value of that time. So let's see that in our next sort of example. So here we have an equation for displacement, or an expression for our displacement. S is equal to 3t to the 4 plus 13t plus 5. And we've been asked here, can we find the instantaneous velocity when t is equal to 3 seconds? So again, if it's velocity that we're after, to get velocity, we need to differentiate our displacement with respect to time. So, well, let's have a go at this one. So if you pause the video here, do you want to try and work out an expression for the velocity? Okay, hopefully you've had a quick go at that. Let's follow our rules. Remember our two rules here. Reduce the power by 1. And multiply by the old power. So that first term, I've got 3t to the 4, so I have 3t cubed multiplied by 3. The second term, plus 13t. Now, if you recall, this is a bit like our special case, right? If we've just got t to the power of 1 or x to the power of 1, the differential would just be the coefficient. So I would just be saying 13 here. And then what happens if we have a constant term, that plus 5? So remember, if we differentiate a constant term, it disappears, right? It means that that term itself does not change as time changes. So the gradient would be 0 for that term. So plus 0. All right, so let's tidy this up. We've got v is equal to 9t cubed plus 13. Okay, so let's answer our question over here. We've got find the instantaneous velocity when time is equal to 3 seconds. So if t is equal to 3 seconds, let's substitute this into our velocity equation. V would be 9 times 3 cubed plus 13. Alright, so let's use a calculator here. So we end up with 9 times 3 cubed, 243, plus 13. So our velocity, well, this is moving very quickly, is not 200, 400, no, sorry, 256. Okay, now assuming that our displacement was in meters to start with, this would be 256 meters per second. So that's moving very quickly indeed. But there we go, that's the answer to our question here.